Friends, I am Amiran Nizami, and today we are going to study a beam problem in Abaqus. So we will use the Abaqus software for solving the beam problem. First of all, we will just solve it analytically. So there is a problem given here that a cantilever beam whose span length is 3 meter and one end fixed and another end is free, and a triangular load is acting in the span of 3 meter, which is uniformly varying load, and at the free end a concentrated moment F naught whose magnitude is 5 to the 5 into 10 to the power 4, and a concentrated moment in the clockwise directions acting whose magnitude is 15000, and all the other datas are given as follows: that the modulus of elasticity is given here, and moment of inertia, and q naught, which is the maximum magnitude at this end, left end, and the span length. So first of all, we know that this beam is a cantilever beam, and it is statically a determinate structure, because we know that the number of reactions here, that for the general load case, the number of reactions developed are 3: one vertical, one horizontal, and one rotational reactions, that's moment. So, and we know that the 3 equilibrium equations are there, so therefore 3 minus 3, that is the degree of indeterminacy, would be equals to 0, and therefore the structure would be a determinate structure. If the structure is determinate, what we know, we can solve it by using the equilibrium equations only. So here we have solved it using the equilibrium equations. Hence there is no horizontal forces acting, so therefore the horizontal reactions would be 0. And then we have started with the vertical reactions. Summation of forces in the y directions is equals to 0, and we have considered the positive direction as upward, so therefore RA is positive acting upward, that would be here, and all other forces are acting in the downward direction, so that would be minus, so that we have taken in the opposite to the equal sides, so that's why it all becomes positive. And then the vertical forces are F naught, so we have also considered F naught, and we know that the uniformly varying load, we have to make it equivalent concentrated load, so we will make it with that half of base into height, that's the triangular way, so half of L into Q naught, so it become equivalent static concentrated load. So therefore we are getting these reactions 8 into 10 to the power 4 Newton. And next the another one, we know that the concentrated moments, so we will see. So here the summation of moments about point A is 0, and we are considering that anti-clockwise is positive, therefore MA, and we know that the M naught here is acting in the clockwise direction, so it is our positive sign, so it's negative, then F naught multiplied by this horizontal length L, and also these equivalent load with the CG, equivalent CG would acting at this point, at this position, which would nothing but L by 3 from this span. So we have just seen here that in this force M naught minus F naught into L minus this load at a distance L by 3 from that left span is acting, that would be equals to 0. So therefore we will just solve this, and we will get MA equals to 195,000 Newton meter. So this was a very simple problem, and we know that it can be solved with the hand analytically, but we are just going to see with the Abaqus, using the Abaqus software, that how we will solve this problem. So let's start. We will just go to the Abaqus. So it's taking some time, so we will wait for that, and now we will start it with the standard explicit. First we will save this, so it's a save model. We will save this with a name uniformly varying load, uniformly varying load, beam case, that's beam, to remember the name. Now we will say okay. Now we will start the part, the first step. So we are going to make 2D planar, and we will just choose a wire from here, and the size, because it's a meter all the units and the length of the span is 3 meters, so we will take maximum of the 10 for it. We will make it continue. Now we will choose the coordinate, so we will choose 0, 0. That's the origin for that. So it is shown here that we have chosen 0 0 at this space origin, and then we know that the length of the span is 3 meters, so we will choose x is 3 comma 0. So the next point would be shown here, so it's shown already here. Okay, so now we will connect these 2 points here. So we will connect here with this help. So these 2 points are connected. We will escape from here and we will just done. Now we will go to the second step and we will go for the property. So first we will fill the property here and we will go to mechanical. So we will click on mechanical, elasticity, and then we will click on elastic. So properties here, E, modulus of elasticity. So we have just seen here that what was the value of the E value. So the E value was given here, it's given data, so 200 E9. So the value here given 200 E9. So we will just feed that data. So let us just feed this value here. So 200 E9, 200 E9, and now Poisson's ratio here 0. So now we will go to the next step and we will just select the section. We will choose beam here. We will just make continue. So here we will just choose the rectangular section. We will make it continue. And what's the value of A and B? So we will see the data here, what's given here. A and B are not given, but only the moment of inertia is given. So we know that the moment of inertia is nothing but the sectional properties of a beam. Okay, so we will choose the sectional properties from here. So how we can get the A and B? If we choose the section as a rectangular, so rectangular means we are considering a square. So I for the rectangular section is BH cube by 12. So what we can do, we can choose the section from there in that manner. So we were just giving the values of the A and B. So we know that the cross section area has not been given here in this. So the moment of inertia is given here, I equals to 30 e to the power minus 6. So we can do one thing, that from this we can find out the A and B. So I is BH cube by 12. So if B equals to H, width and depth is same, so from there we will find out B, and then we will do the rest. So what we know, that BH cube, so that is 12 multiplied by 30 E minus 6. So let's enter, and then we can do one thing, ans to the power 0.25 means 1 by 4. What's the result? 0.1377. So we can feed here the data in Abaqus. 0.1377. 44 means we can just make 0.13774. So okay, now it is over. Okay, so now we will do, we have beam and continue. Sorry, we have already done this step. No, because we have already given one section we have chosen from here. Now I will assign this section. So let's assign, select the region. So we have selected the regions, done. So this section 1. Okay, so we have assigned the section. Now we will just assign the traction. So select the beam orientation, so we will just select, done, just we will click enter. Okay, now we will go to the assembly part. Just click here, because it's only one part. We'll just say okay, then a step. So let's see, create a step. We are having the static forces only, so static force, continue. Then we will just click okay. We'll just go here, see, edit. So stresses has been chosen. Okay, strains, so we don't want these plastic strains right now. Any plastic, only elastic strain components is sufficient for us, so we will just choose that. Displacements, so ut and ur only it is required. And forces and reactions, so we require the reaction forces, reaction moments, and we can say shear forces and moments we can select here. So we didn't require the contacts here, and go okay, dismiss there. Now we will go to the load. We'll just create the load. So load 1, so first is the triangular load or uniformly varying load. So triangular load, so for that triangular load we will go to the line load here. We'll click line load, continue, select the bodies for the load, so we will load on that, done. Now we will choose from here analytical field. Okay, so we know the variation of the varying load, 1 minus x by 3, so it is x here. We will choose x, divided by length is 3 spans, 1 minus x by 3. Choose with the bracket also for a better understanding. So it is chosen. Okay, now component, so in the y direction is component 2, so it is acting in the downward direction, so we will take it minus sign. And what is the value of the q naught? So the maximum magnitude, so we can see here q naught is 2 into 10 to the power 4, so we can give 2e4. So it's chosen here with this, and it is analytical field. Will choose here from there, 2e4, done. So it is a triangular load which is uniformly varying. Okay, now for the next step, the next load 2, what we know, we will just give concentrated force. So concentrated force, and that force is acting at the right end or free end, we know, so we will choose it, done. Then it is asking that what is the value of that concentrated force. So that force is acting in the downward direction, so it is minus sign, and with a magnitude, so we will see the magnitude here. So the magnitude of the concentrated force F naught is 5e4, so we'll give 5e4, means 5 into 10 to the power 4. Okay, so we'll just click okay. So here it has been shown that a magnitude of 5e4 concentrated force is acting in the downward directions. Now the third load is acting, and that third load is concentrated moment, cons moment. So we will just go to the moment, and we will just click continue. We will select the position, so only at this node, right hand node, it's also acting, so we will just do done. And now it asking CM3. So we know that the sign convention which we should remember, that the Abaqus takes anti-clockwise direction as positive. So therefore for the clockwise direction, because our load is acting in the clockwise direction, so we can see from here, it's clockwise, so we will just give minus of what is the magnitude here. So magnitude of m naught is 15000, so we will just give 15123, and we will just give follow the nodal rotation and okay. So a moment is also acting at this edge. Now the next step, create the boundary condition. So we know the boundary condition, left edge, left end, so we will just displacement rotation, so continue. So we will select this end, done. So left end is fixed in our problem, we can see the problem here. So the problem, it's the left end is fixed, so just the cantilevers are fixed, u1 u2 and rotation is all fixed, just will say okay. So here we can see it has been fixed now, and a load, uniformly varying load is acting on this, as well as a moment, concentrated moment, and the concentrated forces in the downward direction. So these are the complete geometry which were acting. So now we will go to the next, which is mesh. So we will just click here, so it will dismiss. We will again go click to the part, again we will just click to the mesh, and then we will just click here. So it's 0.3, we can make much more finer mesh, so we can just take 0.1, so apply and okay. Now we will click mesh part, and we will say okay to the mesh part, and then we will just click here, assign the element types. So we will just select the regions to be assigned, so we will just select, it's done, and it is beam here, and the geometry we know that is linear, means Lagrange interpolation function is there for the geometry, and for the field variables here it is the cubic formulation, means Hermite polynomials. So here it is a Lagrange polynomial for the geometric order, and for this it is cubic formulation for the shape functions for the displacement or field variables. So we will just click here, okay, done. Now we'll just go to the job, and we'll create a job, continue, okay. Now let's check the data check. It will take some time. So data check completed. Now we will submit. So it is submitting right now, it's running, it will take some time. So it has been completed now. So now for the results we will see. So we will just here plot contours on the deformed shape, so we will just click on it. So it is showing the deflected shape in this manner. So it is the von Mises stresses, that how the stresses are distributed, that the maximum magnitude of order 8 4.4 to 8 is acting at red, so at this end. So we know that the fixed end is having the maximum stresses there, and then it is varying, and the minimum stresses are acting at the free end. But we are first interested in the reactions. So the reactions, RT is the transverse reaction, means vertical reaction. So here this point at the left end, 8 into 10 to the power 4 is acting, means this is the vertical reactions acting here. And we can see from the results that what we have found, that RA, so RA was 8 into 10 to the power 4, so we got that value here, that 8 into 10 to the power 4 at the left end, which is the maximum magnitude. And the next we will see the moment, reaction moment. So rm3 is the reaction moments. So let's see, rm3 1.95 to 10 to the power 5. So we will just go and see the reaction moments. What's the here we have solved, but it's not acting somehow. So we can see 19500 here. So the moments acting here is 195 the power 10 to the power 5. So we have got the reactions, and we can see all the displacements. So this is the displacement showing. So it is of this order 9.5 to 7 10 to the power minus 2, and it is here. So deflected shape at each point. So the maximum deflection is of this 9.5 to 7 to 10 to the power minus 2. So it is here, it's showing that the maximum displacement is occurring at this point, and it is reducing with that. And the blue color here we can see the zero displacement. So here at this end no deflection is there. So it's completely giving us the result. So we can see that we are getting this. So we can also zoom it. So the deformed shape of this cantilever beam has been shown here. So thank you.